Hello there, and welcome to the Sleepy Science Documentary Podcast. Tonight we'll be exploring the remarkable and strange world of ice in space, the frozen architects of distant worlds, and the cosmic scaffolding that built everything we see beyond our atmosphere. Ice exists in places we barely understand, in forms that defy what we think we know about water and cold. It clings to grains of dust in molecular clouds where new stars are born. It caps mountains on planets trillions of miles away. It erupts from moons in geysers of pristine beauty. And it drifts through the endless dark as the memory of ancient creation. Some of this ice holds the building blocks of life itself. Other ice forms in ways that should be impossible, yet there it is, waiting to be discovered by those patient enough to look. We'll journey through the outer reaches of our solar system and beyond, following the quiet work of frozen water as it shapes worlds and tells the story of how the universe came to be. If you enjoy these slow and curious journeys through the cosmos, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one peaceful observer at a time. But for now, just breathe. Let the weight of the day fade away and allow your mind to drift toward the distant cold places where ice silently persists. Far beyond Earth's protective warmth, ice behaves in ways that seem almost impossible when we think about frozen water as we know it. In the vacuum of space, the normal rules that govern ice and liquid water on our planet no longer apply. The properties of water change dramatically when exposed to the low pressures and extreme cold of the cosmic environment. When liquid water is somehow placed into the void of space, it experiences two competing forces at once. The vacuum causes the water to want to boil and expand into gas, desperately seeking to become vapor and escape. At the same time, the extreme cold of space pulls the water toward becoming solid ice, freezing the molecules in place. These forces act simultaneously, creating a strange choreography where water boils first, using the remaining heat of the liquid to vaporize in the vacuum. But as this vaporization happens and removes thermal energy, the temperature drops so rapidly that the escaping vapor freezes directly into solid crystals through a process called deposition. This is similar to how dry ice behaves when it transforms from solid directly to gas without ever becoming liquid in its normal phase. The result is both boiling and freezing occurring at the same moment, a paradox made possible only in the extreme environment of space. This simultaneous boiling and freezing is one of the first strange truths about ice beyond Earth, a fundamental difference that shapes how water ice behaves in the cosmic vacuum. The heart of where most space ice forms lies in regions we call molecular clouds. These vast chambers of cold and darkness exist throughout our galaxy, places where the temperature plummets to merely 10 degrees Kelvin, which translates to minus 263 degrees Celsius. In these almost incomprehensibly cold regions, tiny dust grains no larger than particles of smoke float in the darkness. Molecules collide with these grains and stick, building up layers of ice through a process that takes countless generations to complete. Each collision adds a microscopic layer of frozen material to the grain's surface. The icy mantles that form on these dust grains can grow to astonishing thicknesses, reaching more than 100 layers deep, each layer a record of a past molecular collision. Water ice dominates these coverings, but other substances accumulate as well. Carbon monoxide, carbon dioxide, and methanol all contribute to the exotic coatings. These layers build slowly, grain by grain, molecule by molecule. This long-lasting process has been occurring throughout the universe for billions of years, creating vast reservoirs of ice that will eventually help seed new planetary systems and the worlds where life might one day flourish. These dust grains covered in ice become something extraordinary. Scientists now understand that they function as chemical factories, places where complex chemistry happens despite the impossibility of such reactions at these frigid temperatures. Radiation in the form of cosmic rays and ultraviolet light penetrates even into the dense regions where most clouds shield themselves. This radiation bombards the icy mantles, breaking apart simple molecules and recombining them into more complex forms. The reactions create compounds that seem impossible, yet they appear again and again. Complex organic molecules form on these icy surfaces, and these molecules are precisely the building blocks of life itself. Amino acids, the components that build proteins, form in this frozen darkness. Sugars, the molecules that store energy in living things, appear in these chemical factories. Even the bases that comprise DNA and RNA, the genetic codes of life, emerge from the cosmic ice. Formaldehyde, cyanide, and other reactive compounds join these molecules in the growing complexity of the icy mantle. This remarkable process suggests that the ingredients for biology may be formed almost everywhere in the universe, floating on grains of dust waiting for the day they might be incorporated into a world where life could emerge. The implications are staggering. The universe itself may be scattered with the raw materials for life, waiting only for the right conditions to kindle biology into existence. Recent observations have transformed our understanding of where ice exists in our galaxy and beyond it. NASA's SPHEREx mission, launched to map the universe and study its earliest epochs, has also turned its instruments toward cataloguing ice in regions never before examined. The mission has mapped water, carbon dioxide, and carbon monoxide ices across regions of our Milky Way galaxy more than 600 light-years across. Inside giant molecular clouds, where stars are actively forming, the instrument has revealed the precise distribution of frozen water in 3 dimensions. These observations, completed just months ago in April of 2026, represent a transformative moment in our knowledge. The ices attached to the surfaces of dust particles so small they cannot be seen individually. Particles comparable to soot from a candle flame, yet crucial for cosmic chemistry. The dense regions of dust provide crucial protection, shielding these ices from the intense ultraviolet radiation that streams from newborn stars. What these maps reveal is staggering beyond comprehension. Vast quantities of water ice exist in star-forming regions throughout our galaxy, more than astronomers had estimated. Newly formed planetary systems will have access to abundant water resources for oceans and atmospheres. The implications stretch toward understanding whether other worlds might develop oceans and the chemistry necessary for life to emerge and flourish in distant systems. Dark comets represent a mystery that challenges everything we thought we knew about where ice can survive in the solar system. These objects combine characteristics that shouldn't normally coexist in any reasonable model. Asteroids, which orbit closer to the Sun, are rocky bodies without ice, because the warmth of the nearby star would vaporize any frozen water long ago into space. Comets, by contrast, are icy bodies that reside far from the Sun in frigid orbits where ice remains stable and protected. Dark comets, however, break this pattern in ways that science is still struggling to explain. They orbit relatively close to the Sun like asteroids, yet they contain significant quantities of ice hidden beneath their rocky surfaces in protected interior pockets. When astronomers examined 7 dark comets in detail, the findings were startling and unexpected. Between 0.5% and 60% of all near-Earth objects could be dark comets, suggesting far more ice exists in the inner solar system than anyone previously imagined possible. These objects hide in plain sight by not displaying the characteristic coma and tail that makes comets so visibly spectacular to observers on Earth. Their dark surface obscures the ice beneath, making them appear asteroidal rather than cometary. This discovery fundamentally challenges our traditional understanding of the solar system's structure and ice distribution. throughout its various regions. The asteroid belt holds secrets that changed planetary science. Main belt comets orbit within the asteroid belt itself, in the region between Mars and Jupiter, where thousands of rocky bodies circle the Sun. These comets have circular orbits aligned with the plane of the planets, indicating they formed where they now reside rather than migrating from the distant outer solar system. This was unexpected. The asteroid belt, in the conventional understanding, should be too warm for ice to survive. Yet here exist bodies that contain hidden ice, preserved in protected pockets where they have survived for billions of years, shielded from the sun's warmth by overlying layers of dark rock. When collisions occur in the asteroid belt, a common event in this crowded region, smaller bodies strike these icy asteroids and knock away the surface dirt, exposing the hidden ice beneath. The exposed ice immediately begins to sublime in the warmth of the inner solar system. Once the ice is exposed and the asteroid happens to approach closer to the Sun, solar radiation vaporizes the ice more dramatically, creating a coma and tail and transforming the asteroid into a comet in spectacular fashion. These hybrid objects suggest that primordial ice became trapped within the asteroid belt during the solar system's formation, embedded in asteroids and preserved through cosmic ages in pockets and cavities where sublimation never fully occurred. The discovery of these ice-laden asteroids rewrites our understanding of the solar system's earliest days. Beyond Mars and Jupiter, the moons orbiting our solar system's outer planets display ice in its most diverse and wondrous forms throughout the vast reaches of space. Europa, one of the 4 large Galilean moons orbiting Jupiter, represents one of the most remarkable discoveries in planetary science and astrobiology. Scientific consensus has firmly established that deep beneath Europa's surface lies a global ocean of liquid water, hidden from direct observation, yet revealed through careful analysis. Robotic spacecraft, including NASA's Galileo probe and the Cassini orbiter, have provided the evidence through careful observation and detailed analysis of these distant worlds and their properties. Europa's icy crust, as imaged by NASA's Juno mission and its powerful JunoCam instrument, displays an intricate web of fractures and dark markings crisscrossing its surface like a shattered window. The thickness of this icy shell is estimated between 15 and 25 kilometers, a vast frozen layer sitting atop an ocean that may contain more liquid water than all of Earth's oceans combined, making it one of the solar system's largest bodies of water. This subsurface ocean exists in conditions we barely understand, keeping water liquid in the deepest cold through mechanisms we're only beginning to comprehend through observation and theoretical models. Beneath that frozen crust, an entire ocean stretches across Europa's interior, isolated from the outside universe and hidden from our direct view. The ocean remains liquid because of tidal heating, the persistent flexing of the moon as it orbits massive Jupiter. The gravitational pull of the giant planet creates bulges on Europa's surface that shift as the moon rotates. This constant deformation creates friction within the moon's interior, generating heat through mechanical processes. The ocean benefits from this internal warmth, allowing water to remain liquid despite the moon's distance from the sun. Scientists have detected evidence that water vapor plumes erupt from Europa's south pole, shooting material from the subsurface ocean into the thin atmosphere above. This discovery suggests that material from the hidden ocean occasionally reaches the surface, providing an extraordinary opportunity. Future spacecraft might be able to sample the ocean water without drilling through the thick ice shell. The possibility that life could exist in Europa's dark ocean, sustained by chemical energy from hydrothermal vents in the ocean floor, has captivated astrobiologists and space agencies worldwide. Saturn's small moon, Enceladus, represents an even more dramatic example of ice in motion. Despite its size of roughly 500 kilometers in diameter, Enceladus has captivated planetary scientists and fundamentally changed our understanding of icy moons. The Cassini spacecraft, which orbited Saturn for 13 years, discovered something extraordinary. Enormous plumes of water vapor, gases, salts, and ice erupt from cracks at Enceladus's south pole, shooting hundreds of kilometers out into space in spectacular fountains. This phenomenon, called cryovolcanism, represents water geysers on a scale that defies expectation from such a small body. The plumes occur through tiger stripe cracks, distinctive linear fractures where subsurface liquid water forces its way to the surface and vaporizes violently in the vacuum. The thin atmosphere of Enceladus is composed almost entirely of water vapor emanating from these plumes, creating a tenuous veil of frozen material. The icy material and aerosols distributed across the moon's surface by these fountains accumulate over time, creating a slow rain of particles across the icy landscape. Scientists analyzing the plume material have detected organic molecules, complex carbon compounds that represent the chemical building blocks of life. The subsurface ocean beneath Enceladus's ice, kept liquid by tidal heating from Saturn, appears to contain not only liquid water, but also the chemistry and energy sources necessary for life. The discovery of these plumes suggested that we need not drill through miles of ice to study an alien ocean. The mechanism that keeps subsurface oceans liquid on distant moons operates throughout the outer solar system in fascinating ways. Beyond Earth's orbit, the sun's warmth becomes insufficient to keep water in liquid form through direct heating. The planet and its moons receive barely enough solar energy to prevent everything from freezing solid. Yet many of the icy moons in the outer solar system maintain liquid water oceans beneath their frozen surfaces through internal processes. The solution lies in tidal heating, a process as fundamental as the moon's orbit itself and the dance between moon and planet. When a moon orbits a massive planet, the gravitational pull of that planet creates two symmetrical bulges on the moon's surface, one facing the planet and one on the opposite side. As the moon rotates in its orbit, these bulges remain fixed relative to the planet, meaning material on the moon's surface constantly shifts position relative to the gravitational bulges. This creates perpetual flexing and deformation, as if the moon were a rubber ball being squeezed and released continuously in an endless rhythm. The internal friction from this deformation converts gravitational potential energy into heat through mechanical processes. The effect is similar to how a rubber racquetball warms when repeatedly compressed and deformed by a hand. This mechanism, known as tidal friction, becomes the primary energy source maintaining liquid water oceans on distant moons where the sun's heat cannot reach. Europa displays further evidence of cryovolcanic processes that might transport material from its subsurface ocean to the surface in ways we're only beginning to understand. Dark patches appear around surface cracks on Europa, regions enriched with organic molecules that hint at deeper chemistry. These deposits might originate through upwelling from the ocean below, where subsurface liquid water carries dissolved compounds from the depths and chemical energy sources. Alternatively, radiation at the surface might trigger organic chemistry in the ice itself, creating the organic-rich material we observe through spectroscopic analysis. The question remains open, inviting future investigation. But the presence of these organic-rich deposits near surface cracks suggests that cryovolcanic activity occurred in Europa's recent past, or may continue intermittently, even now, in ways we cannot yet directly observe. Such activity could bring nutrient-rich water from the subsurface ocean into contact with the radiation-rich environment of the surface, creating conditions that might support exotic chemistry or even biological processes unlike anything on Earth. The implications stretch toward understanding how life might emerge in the universe's most isolated and extreme environments. Saturn possesses more than one icy moon of exceptional interest. Titan, the ringed planet's largest moon, spans 5,150 kilometers across, making it larger than the planet Mercury itself. Unlike Europa or Enceladus, Titan possesses a thick atmosphere, something unique among icy moons. This atmosphere consists primarily of nitrogen, with significant quantities of methane. Titan's surface conditions are fundamentally different from other icy worlds because it maintains stable bodies of liquid on its surface. The Cassini-Huygens mission discovered vast lakes and seas filled with methane and ethane, particularly concentrated around Titan's north and south polar regions. These polar lakes and seas may exceed 100 meters in depth. The North Pole, explored by Cassini's radar instruments, showed the greatest abundance of these lacustrine features. Titan represents a completely different paradigm from Earth, where the entire hydrological cycle operates with liquid methane and ethane instead of water. Rain falls from methane clouds, precipitation of organic liquid that accumulates in basins and flows across the surface. This strange world of frozen nitrogen bedrock and methane seas represents one of the solar system's most alien and wondrous places. Pluto, despite its demotion from planet status, possesses the most exotic ice formations in the entire solar system. The distant world's surface varies dramatically across its landscape, featuring regions dominated by different types of ice that create a patchwork of crystalline material, unlike anything else known to science. Frozen nitrogen and methane coat portions of the surface, with deposits of water ice forming mountains and ridges of extraordinary height. The bedrock itself consists of water ice so cold that it behaves like solid rock, far harder than stone at such temperatures, nearly as hard as granite or basalt. The mountains on Pluto rise from this frozen water ice foundation, creating peaks that gleam in the faint light of the distant sun, sometimes catching the reflected glow of distant stars. Snowcaps of nearly pure methane ice crown Pluto's mountains, with traces of nitrogen ice mixed through. Out. The mountains display colors shifting from pale whites to subtle browns and reds, painted by chemical reactions driven by Pluto's thin radiation environment. Dunes appear across Pluto's surface, formed from grains of methane ice that originated in the mountains and were carried by wind, though nitrogen ice particles represent another possibility. These dunes are composed not of sand as on Earth, but of ice particles shaped and transported by atmospheric winds despite Pluto's incredibly thin atmosphere. The atmospheric pressure on Pluto is 100,000 times lower than Earth's atmosphere, yet wind-driven processes still mobilize these ice particles into dune formations that march across the frozen landscape in slow migration. The James Webb Space Telescope recently detected an unexplained absorption signal appearing simultaneously on the surfaces of Pluto and Titan, two worlds vastly different in every other regard. Both icy worlds show an identical dip in their light spectra at precisely the same wavelength, yet no confirmed molecule in the laboratory matches the signal. The two worlds share remarkably little in common except one fundamental fact. Both possess chemistry built on methane and nitrogen. On both worlds, sunlight drives methane and nitrogen to react with each other and with other molecules, building heavier and more complex organic compounds. This process paints both worlds in muted reddish-brown tones, the color of complex organic material accumulating across their surfaces. The presence of this identical spectral signal on two bodies with such similar exotic chemistry suggests that the same kind of chemical processes produce the same kinds of material on both worlds. This observation from the James Webb Space Telescope, made just over a year ago, reveals that processes we don't yet fully understand occur on these distant icy worlds, creating molecules that don't match any compounds known from laboratory studies. The reason it remains unidentified is straightforward. Researchers compared the spectral feature against known compounds and the ices expected on these surfaces and nothing fully matched. There is a clear, unmistakable dip in the light, and no confirmed molecule yet reproduces it. Ice in the cosmic environment exists primarily in an amorphous state, rather than as organized crystals. When water molecules cannot freely move and settle into energetically favorable positions at extremely low temperatures, they form what scientists call amorphous water, a solid state lacking the ordered crystalline structure of ice as we know it on Earth. Vapor deposition of water onto cold substrates below 100 Kelvin in a vacuum typically produces this amorphous form. Infrared astronomical observations studying ice in molecular clouds reveal that ice there is predominantly amorphous, identified by the absence of the sharp spectral peak at 3230 wave numbers that characterizes crystalline ice. Amorphous solid water, or ASW, represents the most common type of ice in interstellar and cometary environments throughout the galaxy. The distinction between amorphous and crystalline ice is crucial because it fundamentally affects the ice's physical and chemical properties. Amorphous ice behaves differently from crystalline ice in terms of how it interacts with radiation and how readily chemical reactions proceed on its surface. Most ice throughout the interstellar medium exists in this amorphous state, lacking the organized atomic structure that Earth's ice naturally forms when frozen water gradually cools. Radiation continuously processes space ice, transforming its chemical composition over vast stretches of time. Several sources of energy exist in the interstellar medium, including ultraviolet radiation from distant stars and cosmic rays, high-energy particles that penetrate even into the densest cloud cores where ice forms. Cosmic rays and secondary electrons excite hydrogen molecules in these clouds, producing an internal ultraviolet radiation field within the clouds themselves. Evidence indicates that radiation drives chemical reactions on the surfaces of the icy Galilean moons Europa and Ganymede. Ganymede, notably, is the only moon in the entire solar system to possess its own magnetic field, which creates auroras at its poles similar to Earth's, and scientists can produce laboratory beams of ions to simulate the solar wind and planetary magnetosphere effects and study their impact on icy moon surfaces. Radiation processing represents a crucial mechanism by which ice in space undergoes chemical modification. Energetic particles and photons damage the ice lattice structure, breaking apart simple molecules and creating reactive species that can combine in entirely new ways. This process occurs at atomic scales invisible to our eyes. Over geological timescales spanning millions and billions of years, radiation processing fundamentally alters the chemical composition of space ice, creating exotic materials and compounds found nowhere else in the universe. Water ice throughout the galaxy and universe originated from a common source billions of years in the past. Researchers have established that ice reservoirs attached to the surfaces of tiny dust grains represent the primary location where the universe's water forms and accumulates over cosmic ages. The water in Earth's oceans, the ices in comets, and the frozen material covering planets and moons across our galaxy originate from these interstellar ice factories where chemistry builds slowly. The outer regions of our solar system's asteroid belt may have supplied some of Earth's primordial water and other volatile substances necessary for life, including biogenic precursor molecules such as amino acids. If ice exists in the asteroid main belt today, it is likely primordial in origin, trapped either at the solar system's formation epoch or during some early chaotic phase of planetary migration and rearrangement. This connection between interstellar ice and the water we drink on Earth reveals a profound cosmic cycle that links us to the stars. Ice formed in ancient molecular clouds billions of years ago was incorporated into our solar system during its formation from the collapse of a molecular cloud. That ice became part of the primordial Earth, contributing to our oceans and making possible the emergence of life itself and all the creatures that followed. The sublimation of cometary ice represents the power that drives comets across the solar system. As a comet approaches the Sun, the ice on its surface undergoes a sudden transformation from solid directly to gas, a process called sublimation that defies the normal liquid phase. This change does more than merely vaporize material. It drags dust along with the escaping vapor, ejecting it into space and supplying the force that propels the comet forward on its orbit. The ice carries dust particles that have been frozen into its structure for billions of years, ancient material preserved in cold and now released. Comets typically possess slight accelerations propelled not by gravity but by the ongoing sublimation of ice, phenomena known as non-gravitational accelerations that subtly alter their trajectories. The sublimation of cometary ice is not a gentle process. Rather, it is violent and continuous, a relentless ejection of material that creates the spectacular tails visible from Earth, even across vast distances through space. As a comet approaches the Sun, solar radiation penetrates several meters into the cometary surface, heating subsurface ice and causing it to vaporize explosively from within. This vaporization releases enormous quantities of trapped dust grains, frozen into the ice structure for ages, creating the distinctive cometary atmosphere, or coma, that makes these objects visible from our world and reveals their ancient origins. Ganymede, Jupiter's largest moon and the largest moon in the entire solar system, possesses an unusual and fascinating feature among all the moons of our solar system. It is the only moon known to generate its own magnetic field, a phenomenon that drives auroral displays at its poles, similar to Earth's own auroras in the polar regions. This magnetic field interacts with Jupiter's magnetosphere to create spectacular auroral light shows at Ganymede's poles, painting the sky in colors we can barely imagine. The existence of this magnetic field is unusual and remarkable because it suggests that dynamic processes occur within Ganymede's interior, possibly convection or other mechanisms that generate magnetic activity from deep within. Ganymede, imaged by the Juno mission as it sweeps through the Jovian system, reveals a world that is far from cold and dead. Instead, it displays a complex geophysical character with active processes shaping its icy surface. The icy moons in the outer solar system, including Europa, Enceladus, Titan, and Neptune's moon Triton, are providing fresh challenges and opportunities for astrobiologists seeking to understand where life might exist beyond Earth in the cosmos. Subsurface oceans beneath ice shells represent a profound expansion of the habitable zone as we understand it. The icy moons in the outer solar system, positioned far beyond the traditional habitable zone where sunlight remains sufficient to sustain liquid water, could still harbor life in their subsurface oceans. This departure from conventional thinking challenges what scientists have traditionally viewed as the best places to search for life. If the subsurface oceans in Europa and Enceladus prove to be genuinely habitable environments, the life they could host would almost certainly consist of simple, single-celled organisms like bacteria, organisms sustained by chemical energy rather than sunlight. Some scientists argue that sufficient oxygen forms in the surface ice through radiation-driven processes to potentially support more complex, multicellular life forms. The existence of subsurface oceans beneath ice shells expands our conception of where life might exist throughout the universe. The combination of liquid water, chemical energy from hydrothermal vents or other internal processes, and organic compounds assembled through radiation chemistry might create conditions suitable for microbial life or possibly even more complex organisms on these distant worlds. Nitrogen ice appears throughout the outer solar system in combinations with other frozen volatiles in ways we're still learning to understand. Nitrogen in solid form has been directly detected at the surface of Triton, Pluto, and several Kuiper belt objects, including Eris and Makemake, scattered across the frozen reaches of deep space. In the plumes of Enceladus, nitrogen-bearing molecules such as ammonia and hydrogen cyanide appear in the gas phase with an abundance of approximately 1% relative to water, released from the subsurface ocean. Nitrogen ice has been directly confirmed on Pluto and Triton through spectroscopic observations and detailed chemical analysis. Additional evidence for nitrogen ice appears through shifts of methane absorption bands to shorter wavelengths, which occur when methane dissolves at low concentrations within a matrix of solid nitrogen ice. Pluto, Eris, and Makemake display infrared spectra dominated by methane ice, distinguishing them from most trans-Neptunian objects with water ice-rich or featureless surfaces. The bulk volatile composition of both Eris and Pluto is dominated by nitrogen ice rather than water ice, a feature that marks them as fundamentally different from ice bodies closer to the Sun. Nitrogen ice represents one of the less common but significant ice types found throughout the outer solar system, often occurring mixed with methane and other volatiles in complex arrangements that determine the physical state and properties of these distant frozen worlds. Far beyond the orbits of the known planets lies a vast sphere of ice and rock that extends halfway to the nearest star. The Oort cloud represents the outer boundary of our solar system, a realm of extreme cold where billions upon billions of icy bodies drift in eternal darkness. These objects, some no larger than mountains and others as massive as small planets, comprise the remnants of the solar system's formation. They are mostly composed of water ice mixed with rock, drifting in orbits so distant that the Sun appears as nothing more than an exceptionally bright star among countless others. The Oort cloud is the source of long-period comets, icy wanderers that occasionally fall toward the inner solar system when gravitational perturbations knock them free from their distant orbits. The ice in this vast repository has never experienced the warmth that reaches even the farthest planets. At these distances, the temperature hovers just degrees above absolute zero, making the Oort cloud perhaps the coldest place in our solar system. The sheer distance of the Oort cloud, extending beyond even the orbit of Pluto and into the vast black, makes it a place we can barely fathom. Yet the ice within it preserves information about the early solar system, material that has remained frozen and essentially unchanged since the planets formed. Within the dense regions of interstellar space, vast clouds of gas and dust extend for dozens or even hundreds of light years in every direction. These interstellar ice clouds contain far more ice than exists in all of our solar system combined. The clouds are places where gravity slowly draws material together, where pressure and cold create conditions suitable for chemistry on an astronomical scale. Water ice forms continuously in these regions as molecules collide with dust grains and freeze in place. The ice accumulates layer upon layer, building structures that will eventually collapse under their own gravity to form new stars and planetary systems. Within these clouds, multiple types of ice coexist and interact. Some regions are dominated by water ice, while others contain significant quantities of frozen methane, ammonia, and carbon dioxide. The ice serves as a raw material for future worlds, waiting patiently in the darkness for gravitational forces to awaken them into action. These clouds stretch across mind-bending distances, yet they are not uniform or featureless. They contain denser regions where ice accumulates most rapidly and more diffuse regions where ice forms more slowly. The chemical composition of the ice varies from place to place, reflecting local conditions and chemical processes. The clouds represent the cosmic nurseries where new worlds are perpetually being born from ice and the fundamental elements. Around young stars still surrounded by the disks of material from which planets will form, ice plays a crucial role in determining where planets emerge and what they are composed of. The protoplanetary disk, as these disks are called, contains abundant ice wherever the temperature drops below freezing. In the warmer inner regions near the young star, only rock remains. But beyond a certain distance, the frost line, water and other substances freeze solid. This frost line marks the boundary where planetary compositions change dramatically. Inside the frost line, small rocky planets form. Outside it, massive ice giants accumulate enormous atmospheres and grow to tremendous sizes. The ice in the protoplanetary disk provides the building blocks for moons, rings, and the cores of giant planets. Without ice in the right locations, planets form very differently than they would if ice were absent. The structure of entire planetary systems depends on where ice exists and how much ice is present in different regions of the protoplanetary disk. Distant exoplanets, worlds orbiting stars many light years from Earth, display ice in their own remarkable ways. Several of these discovered planets show evidence of thick ice coverings, suggesting that ice-world planets are common throughout the universe. Some exoplanets possess water ice surfaces and subsurface oceans similar to those on Europa and Enceladus, but orbiting distant suns. Others appear to be composed almost entirely of ice and water, planets where the rocky core, if it exists at all, lies buried far beneath thousands of kilometers of frozen water. These ice-covered exoplanets may be far more numerous than rocky planets like Earth, suggesting that ice worlds represent the common state of planets throughout the universe. The existence of so many ice-bearing exoplanets raises profound questions about where life might emerge and what forms it might take. Ice planets could harbor microbial life in subsurface oceans, supported by tidal heating or chemical energy from planetary interiors, creating biospheres completely isolated from any starlight. Certain forms of ice exist under conditions so extreme that they behave in completely unexpected ways. Ice can be heated and compressed until it transforms into exotic phases that possess properties unlike normal ice. These hot ice forms can remain solid even at temperatures where normal water would boil violently into steam. Under the immense pressure found deep within ice giant planets like Neptune and Uranus, water ice compressed to densities far exceeding that of normal ice takes on characteristics that defy intuition. The ice becomes denser and harder, capable of existing at temperatures of thousands of degrees where the pressure is sufficiently great. Some of these hot ice phases may conduct electricity like a metal, despite being solid water. Others flow slowly like a viscous liquid while remaining crystalline solid in structure. The precise properties depend on the exact pressure and temperature, and different hot ice phases exist in different regions of ice giant planets. The existence of hot ice fundamentally challenges our assumptions about what ice should be. We imagine ice as cold and brittle, yet deep within distant worlds, ice exists hot and flexible, flowing under pressure and conducting electricity. The transformation of ordinary ice into these exotic forms demonstrates the remarkable plasticity of water under extreme conditions and reveals just how different ice can be from our everyday experience with frozen water. Beyond the normal ice that forms under ordinary conditions, exists a family of crystalline water structures designated by Roman numerals. Ice 7 represents one of these unusual phases, forming when water is compressed under significant pressure. Ice 7 possesses a cubic crystal structure quite different from the hexagonal structure of normal ice. It can exist at room temperature under sufficient pressure, a remarkable property that ordinary ice lacks. Ice 7 and other high-pressure phases may exist deep within icy moons and ice giant planets. The discovery of multiple ice phases expanded our understanding of how water behaves under extreme conditions. Each phase represents a different arrangement of water molecules, a different dance of molecular bonds that creates distinct properties. Some of these phases are so exotic that they were initially discovered only in laboratory experiments before astronomers realized they likely exist naturally in space. Superionic ice represents perhaps the most remarkable and counterintuitive form of water ice known to science. Under conditions of extreme pressure and temperature, water ice can transform into a state where the oxygen atoms form a crystalline lattice, while the hydrogen atoms flow freely through the solid structure like a liquid. The ice becomes simultaneously both solid and fluid in different aspects of its nature. Superionic ice may exist deep within ice giant planets, where pressures exceed millions of times that of Earth's atmosphere, and temperatures reach thousands of degrees. The discovery of superionic ice's properties through laboratory experiments and theoretical simulations revealed that water can exist in states fundamentally different from anything found on Earth. The implications stretch toward understanding how planetary interiors function and what processes might operate deep within distant worlds. Superionic ice demonstrates that even something as seemingly simple as water becomes infinitely complex when subjected to the extreme conditions present in space. The fact that oxygen atoms can remain fixed in a crystalline structure while hydrogen atoms move freely represents a state of matter that seems to violate our intuitions about what solid and liquid mean. Yet physics permits it, and the evidence suggests that superionic ice truly exists within the interiors of Neptune and Uranus, shaping the behavior and evolution of these enormous worlds in ways we are only beginning to comprehend. Ammonia ice forms in regions where temperatures drop sufficiently low and ammonia molecules accumulate on dust-grained surfaces. Ammonia, a compound of nitrogen and hydrogen, freezes at much higher temperatures than water, meaning it forms ice in less intensely cold regions. Ammonia ice has been detected in molecular clouds and appears to contribute to the icy mantles that coat interstellar dust grains. On some of Saturn's moons and in the atmospheres of ice giant planets, ammonia ice plays significant roles in creating cloud structures and precipitation. Ammonia ice mixed with water ice creates different properties than either substance alone. The two substances can form mixed ices with varying proportions, changing the melting point, density, and crystalline structure. Ammonia hydrate, a compound of ammonia and water, forms stable structures under certain pressure and temperature conditions and likely exists in various locations throughout the solar system. The interaction between ammonia and water ice demonstrates how different frozen substances can combine to create entirely new materials with properties that neither substance possessed alone. The study of these mixtures reveals that ice chemistry in space is far more complex than a simple analysis of individual frozen substances would suggest. Methane ice, already discussed in the context of Titan and Pluto, represents another crucial frozen substance throughout the universe. Methane freezes at even higher temperatures than ammonia, making it abundant in the coldest regions of space and on the surfaces of the farthest worlds. Methane ice can sublime directly to gas when exposed to even small amounts of heat, a property that makes comets and small icy bodies vulnerable to changes in their environment. Methane ice clouds appear in the atmospheres of Jupiter and Saturn, creating visible features in the planet's appearance. Methane ice on Titan creates dunes of remarkable size and beauty, while on Pluto, methane ice snowcaps crown the tallest mountains. The abundance of methane ice throughout the outer solar system suggests that methane-rich material was common during the formation of the solar system and remains a significant component of icy bodies across vast distances from the Sun. Carbon dioxide ice, formed when carbon dioxide molecules freeze solid, appears throughout space in diverse locations. Carbon dioxide is more volatile than water, meaning it sublimates more readily when subjected to warmth. In molecular clouds, carbon dioxide ice contributes to the icy mantles along with water, methane, and ammonia. On Mars, carbon dioxide ice forms seasonal polar ice caps that expand and contract with the Martian year. Carbon dioxide ice appears in comet compositions, and its sublimation contributes to cometary activity as these icy bodies approach the Sun. The mixture of carbon dioxide ice with other frozen substances creates complex phase diagrams that determine which states of matter are stable under particular pressure and temperature conditions. Carbon dioxide ice's behavior differs from water ice in important ways, affecting how icy bodies behave and what processes can occur on their surfaces. The sublimation of carbon dioxide ice from comets creates spectral signatures that astronomers can observe from Earth, allowing them to identify carbon dioxide ice in distant locations. The volatility of carbon dioxide ice makes it particularly important in cometary nuclei, where the sublimation of carbon dioxide may be as important as water sublimation in driving cometary outbursts and creating the characteristic tails that make comets visible to observers. Nitrogen ice flows like a glacier in some regions, where nitrogen accumulates and becomes subject to pressure and gravity. Nitrogen ice, discussed earlier in the context of Pluto and Triton, forms under the coldest conditions found in the solar system and interstellar space. On Pluto, nitrogen ice flows have been imaged by spacecraft, showing that even at temperatures approaching absolute zero, solid nitrogen can move and deform under its own weight. The discovery of nitrogen ice flows on Pluto demonstrated that ice is not always static and unchanging, but can be a dynamic material that moves and reshapes landscapes over time. Nitrogen ice, mixed with methane and water ice, creates the complex terrain of these distant worlds. The behavior of nitrogen ice under extreme cold provides insights into how materials behave when subjected to conditions that seem incompatible with any form of motion or change. The flowing nitrogen ice on Pluto moves far more slowly than glaciers on Earth, advancing only meters per year rather than meters per day. Yet this slow-motion transformation reveals that even material as hard as frozen nitrogen can deform plastically under the weight of its own mass accumulated across vast distances. Carbon monoxide ice, the frozen form of a simple molecule composed of one carbon and one oxygen atom, contributes to the composition of dust grain mantles in molecular clouds. Carbon monoxide ice is less abundant than water or methane ice, but is regularly detected in astronomical observations. Carbon monoxide ice can react with other molecules when subjected to radiation, contributing to the formation of complex organic compounds on interstellar dust grains. The presence of carbon monoxide ice indicates the complexity of chemical processes occurring on the surfaces of these tiny particles suspended in the cold darkness of space. The ice layers that coat dust grains represent a mixture of multiple frozen substances, each contributing its own properties and reactivity to the overall chemical environment. When multiple types of ice exist together in the same location, they form mixtures with properties that differ from any single pure ice type. Mixed ice compositions create more complex phase diagrams, with multiple possible states of matter depending on precise pressure and temperature conditions. A mixture of water and ammonia ice, for example, has a different melting point than pure water ice. Methane and nitrogen ices mixed together create different properties than either substance alone. The various combinations of frozen substances found throughout space create a rich diversity of possible ice compositions. Each mixture behaves according to its own set of rules determined by the molecular properties of the constituent substances and their interactions with one another. Understanding these mixed compositions is essential for comprehending how real ices throughout space behave. Since pure substances are rare, and most natural ices consist of multiple frozen substances combined together, the complexity of these mixtures creates a nearly infinite variety of possible ice types, each with its own unique properties and behavior. In comets, for instance, the exact mixture of water, methane, ammonia, and other ices determines how the comet will respond as it approaches the Sun and begins to sublime. Crystalline structures in ice arise from the ordered arrangement of water molecules in repeating patterns. Ice naturally forms hexagonal crystals, but under different pressure and temperature conditions, Water molecules arrange themselves into different geometric patterns. Some ice phases form cubic structures, others form monoclinic or tetragonal arrangements. Each crystalline structure represents a different way that water molecules can bond with their neighbors, with different angles and distances between molecules. The crystalline structure affects many properties of the ice, including how dense it is, how hard it is, and how it responds to pressure and temperature changes. On Earth, snowflakes form hexagonal crystals because the conditions on Earth favor the hexagonal arrangement. Space. Different conditions favor different structures, creating a diversity of ice crystal arrangements matched to the environments where they form. The study of crystalline structures reveals the underlying physical and chemical principles that govern how matter organizes itself. The fact that water can adopt so many different crystalline arrangements demonstrates that the same basic molecule can create entirely different materials based on how it organizes itself. This principle has profound implications for understanding the diversity of ice throughout the universe and how environmental conditions shape the physical properties of frozen substances. Amorphous ice in space, lacking any organized crystalline structure, represents the most common form of ice in the universe beyond Earth. Amorphous ice forms when water molecules freeze so rapidly that they do not have time to settle into organized crystalline arrangements. Instead, they remain in random positions, creating a disordered solid that resembles frozen glass more than normal ice. Amorphous ice coating, dust grains in molecular clouds, represents the most abundant form of water ice in the universe. The distinction between amorphous and crystalline ice matters for understanding ice chemistry. Amorphous ice is more chemically reactive than crystalline ice, meaning that reactions proceed more readily on its surface. This greater reactivity contributes to the formation of complex organic molecules on dust-grained surfaces. When amorphous ice is warmed, it may crystallize into an ordered form, releasing energy and potentially triggering chemical reactions. The prevalence of amorphous ice throughout space makes it perhaps the most important form of ice for chemistry and biology. In the nebulae where stars form, ice accumulates through a process of ongoing condensation and deposition. Dust grains created from supernova explosions and stellar outflows drift through these nebulae, gradually collecting layers of frozen material. The ice formation is not instantaneous, but occurs over millions of years as molecules collide with grains and freeze in place. The temperature within different parts of a nebula varies, determining which substances freeze and where they accumulate. In warmer regions closer to existing stars, only water ice forms. In colder outer regions, methane, ammonia, and nitrogen freeze as well. The result is a stratification of ice composition matched to temperature gradients. This spatial organization of different ices, based on temperature and chemistry, reflects fundamental principles of how matter behaves under varied conditions. The nebulae serve as enormous cosmic laboratories, where chemistry and physics combine to create the raw materials from which worlds will eventually emerge. The icy mantles that accumulate on dust grains represent one of the most important structures in space chemistry. Beginning with a bare silicate grain, molecules gradually accumulate through collisions and deposition. The mantle grows grain by grain, molecule by molecule, over vast stretches of time. These mantles can exceed 100 layers thick, yet each layer remains only a few molecules thick. Within these mantles, complex chemistry proceeds driven by radiation and molecular collisions. The icy mantles serve as surfaces where chemical reactions occur with far greater ease than in the gas phase. Molecules that would rarely collide in the sparse gas phase can meet on grain surfaces and react. The icy mantles thus function as vast chemical reactors, converting simple molecules into complex compounds. The importance of these mantles for creating the building blocks of life cannot be overstated. They represent the birthplace of complex chemistry in space. Ice's role in planet formation extends beyond simply providing raw material. Ice affects how particles stick together and form larger bodies. Icy particles collide and merge more readily than dry rocky particles because the ice acts like a glue holding particles together. This greater stickiness of icy material means that planets form more readily in regions containing substantial quantities of ice. The location of the frost line determines where ice is abundant and where rocky material dominates. This fundamental fact shapes the structure of entire planetary systems. Rocky planets form in the warm inner solar system, while ice-dominated planets form farther out where temperatures plunge below freezing. The presence or absence of ice in specific regions determines whether giant planets form at those locations. Without ice at the right distances from a star, planetary systems form very differently than they would if ice were abundant. The role of ice in planet formation suggests that ice's influence extends from the smallest dust grains to the structure of entire solar systems. The frost line represents the critical boundary in a protoplanetary disk where the temperature drops below the freezing point of water. Inside this boundary, only rocky material accumulates, creating terrestrial planets. Outside this boundary, ice accumulates along with rock, allowing giant planets to form rapidly by accreting substantial quantities of ice and gas. The location of the frost line depends on the luminosity of the central star and the structure of the disk. For our Sun during the early solar system, the frost line lay somewhere between Mars and Jupiter, allowing Mars to be rocky while Jupiter became a gas giant. The frost line is not a static feature but may move during the evolution of a protoplanetary disk as the disk cools or heats in response to changing stellar output and D-disk processes. The concept of the frost line explains much about planetary system architecture. It demonstrates how the distribution of ice fundamentally determines which kinds of planets form where. Deep within ice giant planets like Neptune and Uranus, ice exists under such extreme pressure that it behaves in profoundly different ways than ice anywhere else. The interior of these planets may consist of a mantle of superionic ice and other exotic ice phases surrounding a rocky core. The pressure within these planets exceeds millions of times that of Earth's atmosphere. The temperature rises to thousands of degrees with increasing depth. Under these conditions, water ice transitions through multiple exotic phases, each stable over specific pressure and temperature ranges. The interior of an ice giant represents a realm of ice that is simultaneously the hottest ice anywhere in our solar system and the coldest interior of any gas giant or terrestrial planet. The behavior of ice under these extreme conditions directly influences how these planets function, how they generate magnetic fields, and how they evolve over time. Understanding ice giant interiors requires understanding how water behaves under conditions never encountered in terrestrial laboratories. When ice is subjected to pressure far exceeding what any known material could withstand on Earth, its behavior becomes even more exotic and remarkable. Pressure not only changes which phase of ice is stable, but also fundamentally alters how ice interacts with other materials. Ice under extreme pressure can flow plastically, deforming slowly under constant stress. Ice can become harder than diamond under sufficient pressure. Ice can become electrically conductive. The extreme pressure environment within planets creates ice with properties that defy our everyday intuitions about what frozen water should be like. The study of ice under extreme pressure requires both theoretical calculations and laboratory experiments that create conditions approaching those found deep within planets. Each new understanding of ice under extreme pressure contributes to comprehension of planetary interiors and the processes that operate there. The universe contains far more extreme forms of ice than the frozen water we encounter in our familiar world. Future missions to explore the ocean worlds of the outer solar system will focus heavily on understanding the ice that covers them. The Europa Clipper mission currently operating in the Jovian system, will perform detailed observations of Europa's icy surface and the structure of its ice shell. The spacecraft carries instruments designed to detect signs of water and potential biosignatures that might indicate life in the ocean below. The mission will help determine whether water plumes erupt from the surface and whether conditions in the subsurface ocean truly support life. The detailed maps of ice composition and structure created by this mission will guide future efforts to study Europa's ocean. The mission represents a crucial step toward understanding whether life exists on an ice-covered world and how the ice shell exchanges material with the ocean beneath. The scientific results from the Europa Clipper will transform our understanding of how ice and liquid water interact on distant moons. The Dragonfly mission, scheduled to arrive at Titan in the 1930s, will explore the methane lakes and organic chemistry of that remarkable moon. Dragonfly is a rotorcraft lander, a vehicle that can fly through Titan's thick atmosphere and explore multiple locations across the surface. The mission will investigate how organic chemistry proceeds under Titan's unique conditions of methane rain, frozen nitrogen bedrock, and complex atmospheric processes. Dragonfly will sample the organic material that accumulates on Titan's surface, seeking evidence of prebiotic chemistry that might reveal how life could emerge on such an alien world. The mission will advance understanding of how methane ice behaves as a planetary surface material and how it interacts with the atmosphere and subsurface. Dragonfly represents humanity's most ambitious effort to explore an ice world unlike anything on Earth. The discovery of complex organic chemistry on Titan could provide crucial insights into whether life might originate in environments far stranger and more extreme than anything found on Earth. The possibility of mining ice in space has shifted from pure speculation to serious engineering consideration. The ice in the Oort cloud and asteroid belt represents an enormous reservoir of water and other volatiles that could potentially be extracted and utilized. Water derived from space ice could be used as rocket fuel, providing the fuel needed for deep space missions without the massive cost of launching water from Earth. Mining ice from asteroids or comets could provide resources for establishing settlements on the Moon or Mars. The technical challenges of mining ice in space remain substantial, but the potential benefits have sparked serious research and development efforts. The prospect of extracting ice from space raises profound questions about resource utilization in the solar system and the future of human expansion beyond Earth. The abundance of ice throughout space suggests that water and other volatile substances will eventually become crucial resources for space exploration and settlement. Ice can be converted into rocket fuel through chemical processes that split water molecules and recombine them with other elements to create propellants with high energy content. Hydrogen and oxygen derived from water ice through electrolysis can be combined to create high-performance rocket fuel. This fuel has higher specific impulse than chemical fuels derived from fossil sources, meaning it can propel spacecraft with greater efficiency. The possibility of producing rocket fuel from ice extracted from space resources offers the tantalizing prospect of establishing fuel depots in space that could support deep space missions without relying on launches from Earth. Spacecraft could refuel at these depots, extending their range and enabling missions that would otherwise require enormous payload launches from Earth. The use of space ice as a source of rocket fuel represents one of the most promising approaches to sustaining long-term space exploration. The abundance of ice throughout the solar system means that fuel derived from ice resources could potentially sustain an entire civilization operating in space. Ice in space holds profound significance for astrobiology, the study of life beyond Earth. Ice contains the organic compounds and water necessary for life as we understand it. Ice in the form of icy mantles on dust grains appears to be the birthplace of complex organic molecules throughout the universe. These molecules may be precursors to biology, chemicals from which life could eventually emerge under the right conditions. Ice preserves organic material from destruction by radiation and stellar processes. Comets and meteorites that delivered ice and organic compounds to early Earth may have delivered the raw materials from which terrestrial life ultimately emerged. The study of ice in space thus becomes central to understanding how life originated and whether life might exist elsewhere in the universe. The molecules found in space ice suggest that the chemistry of life is not unique to Earth, but rather a natural consequence of the chemistry proceeding throughout the cosmos. Subsurface ocean worlds beneath ice shells represent some of the most promising locations in the solar system where extraterrestrial life might exist. Europa's ocean beneath its ice crust, Enceladus's subsurface sea revealed by plumes, and potential oceans on distant exoplanets all represent places where life could potentially flourish. These oceans are kept liquid by tidal heating or other internal heat sources rather than by proximity to the sun. The combination of liquid water, organic material, and chemical or thermal energy provides the basic requirements for life. The ice shells overlying these oceans present both barriers and protection. The barriers prevent direct observation of the oceans from space. The protection shields the oceans from extreme radiation and impacts that would destroy any life at the surface. The study of subsurface ocean worlds has become central to the search for life beyond Earth, focusing scientific attention on places where ice represents not an obstacle, but a necessary component of habitable environments. Ice serves a crucial function as a radiation shield, protecting whatever lies beneath it from the intense radiation streaming from space. On worlds without magnetic fields, radiation from the sun and distant cosmic sources bombards the surface relentlessly. Ice absorbs much of this radiation, preventing it from penetrating deeply into the material beneath. In subsurface oceans, the ice shell shields the liquid water and any life within it from radiation that would be lethal. The thickness of an ice shell determines how effectively it shields the environment below. Europa's relatively thin ice shell, estimated at 15 to 25 kilometers, provides significant protection while remaining thin enough that plumes might deliver ocean material to the surface. The role of ice as a radiation shield demonstrates that ice on distant worlds serves multiple functions beyond simply being a frozen phase of water. Ice creates environments where life might emerge and persist in places that would otherwise be bathed in deadly radiation. Ancient ice records preserve information about the formation and evolution of the solar system and the universe itself. Ice in comets contains trapped gases and dust from the early solar system, material that has remained essentially unchanged since the solar system's formation 4.6 billion years ago. Studying the composition of cometary ice provides direct information about the conditions that existed during the solar system's formation. Ice in interstellar clouds contains evidence of chemical processes that have been occurring throughout the galaxy for billions of years. The isotopic composition of ice in different locations reveals the origins of material and how it has been transported and processed. Ammonia ice, methane ice, water ice, and all the other frozen substances throughout space carry information embedded in their molecular structure about the history of the universe. The study of ancient ice thus becomes a method for reading the history of cosmic evolution written in frozen form. Mars holds frozen water in places where temperature and pressure create conditions unsuitable for liquid existence. The red planet's polar ice caps contain a mixture of water ice and carbon dioxide ice, shifting seasonally as carbon dioxide condenses during winter and sublimes during spring. The presence of water ice suggests that Mars experienced a warmer, wetter past when liquid water flowed across the surface in greater abundance. Scientists studying the composition of these polar caps gain insights into the processes that transformed the planet from a potentially habitable world into the cold desert it is today. The ice caps contain trapped atmospheric samples and dust from different periods of Martian history, preserving records of climatic transitions. Water ice in Mars's polar regions represents a precious resource that future human missions might extract and utilize for fuel and life support systems. Glacial features on Mars reveal the presence of ancient ice in surprising locations. Lobate debris aprons and lineated valley fills appear in numerous regions, characteristics that suggest the presence of ice-rich material beneath the surface. These formations look like glaciers that have been covered by a protective layer of dust and rock, creating frozen features that remain largely unchanged over geological time. The patterns of these features indicate that Mars experienced episodes of glaciation when massive volumes of ice accumulated in particular regions. Radar instruments on orbiting spacecraft have detected subsurface ice within these features, confirming that frozen water persists beneath the surface despite the cold, dry conditions above. The presence of these ice-covered glacial features complicates our understanding of Mars's climate and suggests that the planet may have experienced multiple episodes of ice accumulation and melting. Some scientists propose that enormous quantities of water ice lie hidden just beneath the Martian surface in numerous locations, waiting for future explorers to discover and utilize them. The study of these glacial features has become central to assessing Mars's potential habitability and the feasibility of establishing human settlements on the planet. Mercury's poles hold water ice in surprising abundance for a world orbiting so close to the Sun. The extreme temperatures at Mercury's north and south poles remain cold enough to preserve water ice despite the intense heat in the equatorial regions. Permanently shadowed craters near the poles create thermal refuges where ice can remain frozen indefinitely. The presence of water ice on Mercury suggests that comets or asteroids delivered this material during the early solar system's formation, and that the ice has remained protected within these shadowed regions ever since. Radar observations from spacecraft have mapped extensive deposits of water ice within these polar craters, revealing that Mercury possesses more ice than was initially expected. The ice deposits contain layers of dark material overlying the lighter ice, a configuration that may represent ancient dust from impacts mixed with the ice accumulation. The discovery of water ice on Mercury fundamentally changed our understanding of where ice can survive in the inner solar system, and demonstrated that even worlds orbiting very close to the Sun can harbor significant frozen water reserves if they possess the right topographical features. Venus possesses almost no ice despite its proximity to the Sun and its presence in the inner solar system. The planet's extreme surface temperature, exceeding 460 degrees Celsius, makes the survival of any form of water ice impossible. The thick atmosphere creates a runaway greenhouse effect that heats the surface far beyond the melting point of even exotic ice phases. The absence of water ice on Venus stands in stark contrast to the abundance of ice found throughout the outer solar system and in numerous locations in the inner solar system. Venus likely possessed water during its formation, but the intense solar radiation evaporated the water from the surface early in the planet's history. The solar wind stripped away the hydrogen, leaving behind the oxygen to combine with other elements and create the sulfuric acid clouds that characterize the Venusian atmosphere today. The story of Venus demonstrates what happens to water-bearing worlds when they experience runaway greenhouse warming, a cautionary tale about planetary climate extremes. Venus serves as a reminder that ice is vulnerable and can disappear under sufficiently intense heating. Earth's ice comes partly from sources beyond our planet, delivered by meteorites and comets that struck the early world. The composition of water in Earth's oceans suggests that extraterrestrial material contributed substantially to our planet's water inventory. Analysis of isotopes in terrestrial water reveals ratios that differ from pure solar nebula material, indicating that ice-bearing bodies from beyond Earth's formation region were incorporated into our world. Comets delivering water ice from the outer solar system likely contributed to replenishing the water that escaped from the inner solar system during the planet's formation. Meteorites from the outer asteroid belt, themselves containing ice accumulated during the solar system's early phases, brought additional water to Earth. The water we drink and the oceans in which life emerged thus contain material that originated in regions far more distant than Earth's current orbit, material that journeyed across the solar system before becoming part of our world. The recognition that Earth's water came partly from space ice demonstrates the interconnectedness of the solar system and the way material migrates across vast distances. Our existence depends fundamentally on ice that formed far from the Sun and was delivered to our world by cosmic wanderers. Isotopes trapped in cosmic ice reveal the conditions and processes that occurred during the solar system's formation. Water ice contains different ratios of hydrogen and deuterium, and these isotopic signatures vary depending on the temperature at which the ice formed. Cold regions produce ice enriched in deuterium, while warmer regions produce ice with lower deuterium content. By measuring isotopic ratios in meteorites, comets, and other solar system bodies, scientists can determine where the material formed and how it was transported. Comets arriving from the outer solar system display isotopic compositions that differ from meteorites in the asteroid belt, revealing distinct formation locations. The isotopic analysis of ice in different solar system bodies has revolutionized our understanding of planetary migration and the mixing of material throughout the young solar system. Isotopic variations in space ice also provide clues about the timescale of ice formation and the chemical processes that operated during the solar system's earliest epochs. The isotopes preserved in cosmic ice thus function as a chemical calendar and migration map, documenting the history of material transport across the solar system. Meteorites containing ice fragments carry evidence of conditions in the early solar system preserved in solid form. Some meteorites have remained virtually unchanged since their formation, billions of years ago, suspended in the vacuum of space where chemical reactions proceed extremely slowly. These meteorites contain water ice mixed with organic material, the same combination of ingredients found on the dust-grained surfaces in molecular clouds. The ice in meteorites is often amorphous, lacking the organized crystal structure that water forms on Earth, reflecting the conditions under which the ice formed in the cold regions of the early protoplanetary disk. When meteorites fall to Earth and are analyzed in laboratories, scientists can extract samples of ancient ice and study its composition, the gases it contains, and the organic molecules frozen within it. The ice in meteorites represents material that was never subjected to the heating that occurred on planetary bodies like Earth or Mars, making the meteoritic ice particularly valuable for studying the pristine composition of the early solar system. Meteorites containing ice and organic material suggest that the chemical complexity necessary for life emerged naturally from the inorganic chemistry of space, ice, and dust. Phosphine has been detected in some forms of space ice and interstellar dust, revealing unexpected chemical complexity. Phosphine is a compound of phosphorus and hydrogen that plays crucial roles in the chemistry of life on Earth. The detection of phosphine in space ice suggests that phosphorus-containing compounds form through natural chemical processes in the interstellar medium and accumulate on dust-grained surfaces. The presence of phosphine in cosmic ice raises intriguing questions about the chemical building blocks available in interstellar regions and how readily the ingredients of biology assemble in space. Phosphine may be produced through radiation-driven reactions occurring on ice surfaces exposed to cosmic rays and ultraviolet light. The molecule is unstable in the presence of oxygen, making its detection and survival in space surprising and requiring specific conditions to persist. The discovery of phosphine in space ice demonstrates that the chemical inventory of the cosmos includes rare and significant compounds that participate in life processes on Earth. The presence of phosphine-containing compounds in meteorites and comets suggest that these molecules may have been incorporated into the early Earth and contributed to the emergence of the chemistry of life. Organic compounds of remarkable complexity form through chemical reactions proceeding on the surfaces of space ice. Laboratory experiments simulating the conditions of interstellar clouds demonstrate that complex organic molecules spontaneously form when ice is exposed to ultraviolet light and cosmic rays. The reactions produce compounds with multiple carbon atoms linked together in chains and rings, creating structures far more intricate than simple molecules like carbon monoxide or ammonia. The ice surface provides a stable platform where molecules can collide and react without being torn apart by solar radiation or scattered into the vacuum. As ice accumulates more material through continued deposition, the complexity of the organic molecules increases, creating a hierarchy of increasingly sophisticated chemical structures. The organic compounds detected in meteorites and comets likely originated through these ice surface chemical processes in the early solar system and in molecular clouds. The diversity of organic compounds found in space ice suggests that the chemical foundation for life assembled naturally through the physics and chemistry of frozen dust. The organic complexity achievable through simple radiation-driven reactions on ice surfaces rivals what living organisms create through biochemical processes, suggesting that the boundary between chemistry and biology may be less distinct than traditionally conceived. Laboratory studies have conclusively demonstrated that amino acids precipitate from solutions containing simple organic compounds when exposed to radiation and heating. The experiments simulate conditions likely present in the early solar system and in meteorite-forming regions. Amino acids have been detected in meteorites that fell to Earth, with isotopic compositions confirming their extraterrestrial origin. The diversity of amino acids found in meteorites exceeds 50 different types, many of which are used by life on Earth. The synthesis of amino acids in space ice demonstrates that the chemistry of life emerges naturally from non-biological processes in the cosmos. The amino acids formed in space ice would have been incorporated into the early Earth through meteorite and comet impacts, providing a ready supply of these essential molecules for the origin of life. The presence of amino acids in interstellar dust grains and space ice throughout the galaxy suggests that the chemical ingredients of life are distributed abundantly throughout the cosmos. If life emerges anywhere in the universe, it likely builds on the foundation of amino acids and organic molecules that form spontaneously in space ice. Ice can become fossilized when it becomes buried beneath protective layers of sediment or other material that shields it from sublimation and decomposition. When ice becomes trapped in geological structures or protected by overlying material, it can persist for extraordinary periods of time, essentially becoming preserved in a frozen state. Ancient ice can develop distinct properties as it ages, with crystal structures transforming and chemical compositions shifting slightly over geological timescales. Some buried ice deposits have persisted for millions of years in protected environments, creating a fossil record of ancient climate conditions. The study of fossilized ice provides direct evidence of the temperatures and atmospheric compositions of ancient periods. Ancient ice cores retrieved from glaciers and permafrost regions contain trapped air bubbles and dust that reveal the conditions when the ice formed. The frozen remains of organisms and organic material preserved in ancient ice provide glimpses of ecosystems that disappeared long ago. Ice fossilization demonstrates that frozen water can function as an archive of planetary history, preserving information about past climates, atmospheres, and life in a way that few other materials can match. Ring systems surrounding the giant planets consist largely of particles of ice and rock, with the ice making up a substantial fraction of the ring material. The rings of Saturn are predominantly water ice, with particles ranging in size from millimeters to meters across. The icy particles in Saturn's rings are exceptionally pure, with water ice making up a much higher percentage of the ring material than expected based on our understanding of how rings form. The rings of Uranus and Neptune also contain significant quantities of ice mixed with dark material. Jupiter possesses rings that are far fainter and contain more rocky material mixed with ice. The icy composition of these rings suggests that the rings formed from material that accreted in the cold outer regions of the protoplanetary disks surrounding each planet. The icy particles in planetary rings continuously collide and reshape one another, creating a dynamic system where the rings evolve slowly over time. The study of ring composition reveals the composition of the protoplanetary disks and provides insights into planetary formation processes. The age of Saturn's rings remains one of the great mysteries in planetary science, with estimates ranging from young, recently formed systems to ancient rings that have persisted since the early solar system. The pristine appearance and high purity of Saturn's ice rings suggest they may be relatively young, perhaps only a few 100 million years old, having formed after the giant planets reached their current positions. Alternatively, if the rings are ancient and date to the solar system's formation, mechanisms must exist to keep them clean and prevent contamination from infall of space debris. Computer simulations suggest that the rings may have formed when a moon or small planet wandered into Saturn's Roche limit and was torn apart by tidal forces. The icy fragments from this disrupted body would have been spread into a disk that eventually organized into the spectacular ring system we observe today. Recent studies of the rate at which the rings are being contaminated by infalling material suggest that Saturn's rings cannot be older than about 100 million years without accumulating excessive dust and debris. The question of ring age remains actively debated among planetary scientists, with new observations from spacecraft and theoretical calculations continuously refining our understanding. The mystery of Saturn's ring age highlights how much remains unknown about planetary system evolution. The purity of ice in Saturn's rings surpasses that found in most other solar system locations. The ice particles contain less than 5% rocky contamination, an exceptionally low level compared to other ice-rich bodies. The high purity suggests material has not undergone significant contamination since the rings formed, likely from the disruption of an ice-rich moon or comet. The mechanisms maintaining this purity remain incompletely understood, but may involve electromagnetic forces that cause smaller particles to spiral into Saturn. The contrast between Saturn's pure ice and the darker contaminated ice of other ring systems highlights composition diversity. The study of ring ice purity contributes to understanding ring formation and evolution. Jupiter's rings consist primarily of faint material that is far less conspicuous than the bright rings of Saturn. The particles in Jupiter's rings are predominantly dust and small rocky material, with ice playing a lesser role compared to Saturn's rings. The rings of Jupiter are fed by material ejected from Jupiter's small inner moons when impacts eject debris that gradually spirals into the ring system. The faintness of Jupiter's rings results from the small size of the particles, which scatter light far less effectively than larger icy bodies. Despite the faintness and rocky composition of Jupiter's rings, ice particles constitute a fraction of the ring material and contribute to the overall ring structure. Jupiter's main ring displays changes in brightness and structure over time, as the distribution of particles shifts in response to orbital dynamics and gravitational interactions. The faint nature of Jupiter's rings makes them challenging to observe from Earth, requiring spacecraft observations to resolve the ring structure in detail. The study of Jupiter's faint rings has revealed that planetary ring systems exhibit far greater diversity in composition and appearance than the spectacular rings of Saturn would suggest. Uranus's rings appear dark and lacking the brightness and prominence of Saturn's rings. The dark color of Uranus's rings suggests that the material is heavily contaminated with carbonaceous compounds and other dark substances mixed with the ice. The rings of Uranus are narrow and closely spaced, contrasting with the broader rings of Saturn. The darkness and narrowness of Uranus's rings may reflect the youth of the ring system, or the processes that keep the rings confined within narrow corridors. Gravitational interactions with small moons orbiting near the rings may be responsible for maintaining the narrow ring configuration and preventing the rings from spreading and dissipating. The ice in Uranus's rings is likely contaminated and less pure than the ice in Saturn's rings, reflecting different formation or processing histories. The study of Uranus's dark rings contributes to understanding the diversity of ring systems and the processes that shape planetary rings. The contrast between the bright, pure rings of Saturn and the dark, narrow rings of Uranus demonstrates that planetary ring systems can vary dramatically depending on planetary properties and ring formation history. Neptune's rings appear incomplete, consisting of arc segments rather than continuous rings encircling the planet. The arcs of Neptune's rings are asymmetric and unequally distributed around the planet, creating a puzzle for planetary scientists attempting to understand ring dynamics and stability. The icy particles in Neptune's rings are small and dark, similar to those in Uranus's rings in composition and appearance. The arcs may be maintained by the gravitational influence of nearby small moons that confine the particles into limited regions. The incompleteness of Neptune's rings may reflect the relative youth of the ring system and instability that will eventually spread the material around the planet into a more complete ring structure. The ice in Neptune's rings appears to be contaminated with dark material, similar to the ice in other outer planet rings. The study of Neptune's arc rings has challenged theories of ring dynamics and led to new understanding of how gravitational forces can maintain ring material in non-uniform configurations. Neptune's unusual ring arcs represent one of the most striking examples of ring asymmetry in the solar system. Collisions between ice particles in planetary rings produce heat through frictional and impact processes. When particles collide at relatively high velocities, the kinetic energy converts into heat, warming the particles at the point of impact. Multiple collisions occurring simultaneously throughout the ring system generate enormous quantities of heat distributed throughout the ring structure. The heat from particle collisions influences the temperature profile of the rings and may cause surface sublimation in regions where temperatures rise sufficiently. The collision processes influence how ring particles stick together, roll past one another, or bounce apart depending on the collision velocity and particle composition. The detailed understanding of particle collision processes in rings requires sophisticated computer simulations accounting for the diverse sizes, masses, and velocities of the countless particles. The heat generated through collisions contributes to the overall energy budget of the ring systems and influences the long-term evolution and stability of the rings. The study of ice particle collisions in planetary rings reveals the mechanisms that shape the dynamics of astronomical systems. Shepherd moons orbiting near planetary rings exert gravitational forces that confine and organize ring particles. These small moons prevent ring particles from spreading and dissipating by their gravitational influence, essentially herding the particles into organized ring structures. Saturn possesses numerous shepherd moons that maintain various rings through gravitational interactions. The gravitational influence of shepherd moons is particularly important for maintaining narrow rings and arc segments that would otherwise be gravitationally unstable. The interaction between shepherd moons and ring particles involves complex orbital mechanics and results in the organized ring structures that we observe. Small moons orbiting within rings create gaps and structure that reflect their gravitational influence on the surrounding particles. The discovery of shepherd moons revolutionized our understanding of how planetary rings maintain their structure and organization. The relationship between shepherd moons and ice particles in rings demonstrates how gravity can organize matter into complex structures across astronomical scales. Ice spokes are transient features that appear and disappear in Saturn's rings. creating radial patterns that extend from the inner rings toward the outer edge. These spokes consist of fine dust particles suspended above the ring plane, creating shadows visible against the bright icy rings below. The spokes are thought to form through electromagnetic forces operating on small particles charged by solar ultraviolet radiation. The spokes rotate at the rate that Saturn's magnetic field rotates, not at the orbital velocity of the ring particles, indicating that electromagnetic forces rather than orbital dynamics maintain the spoke structures. The spokes appear and disappear over timescales of hours to days, making them transient features that require specific conditions to form and maintain. The mechanism creating spokes remains incompletely understood, though leading theories invoke complex interactions between solar radiation, planetary magnetic fields, and the electrical properties of dust particles. The study of ice spokes has revealed unexpected electromagnetic processes operating in planetary ring systems. The ephemeral nature of spokes demonstrates that planetary rings are dynamic systems where particles be having complex ways governed by radiation and electromagnetic forces as well as gravity. Ice rain falls from Saturn's upper atmosphere onto the ring system, delivering material that may alter ring composition and structure. Observations suggest that particles falling from Saturn's atmosphere reach the rings and merge with the ring material, slowly contaminating the otherwise pure ice. The rain of atmospheric material represents an ongoing process that gradually changes ring composition over geological time. Water molecules subliming from the rings escape into space or recombine with atmospheric molecules returning to Saturn's atmosphere, establishing an exchange cycle between rings and atmosphere. The amount of material exchanging between Saturn's atmosphere and its rings each year remains poorly quantified, but likely influences ring evolution and contamination rates. The discovery of this atmospheric exchange process demonstrated that planetary rings are not isolated systems, but participate in material exchange with the parent planet. The atmospheric material reaching the rings brings both water and other chemical compounds that alter the chemical environment of the rings. Understanding the rates and composition of material exchanging between Saturn and its rings is crucial for interpreting ring observations and predicting ring evolution. Tethys and Dione, two of Saturn's substantial ice moons, display different types of icy landscapes, reflecting their distinct geological histories. Tethys possesses a massive impact basin and numerous smaller craters, with the large crater Odysseus dominating one hemisphere. Dione displays cratered terrain similar to Tethys, but also features linear valleys and ridges that suggest tectonic activity in its past. Both moons possess icy surfaces with subsurface compositions that likely include rocky material mixed with ice. The density and crater distributions suggest that both moons have experienced substantial bombardment and geological evolution. Tethys possesses a massive ocean that likely lies beneath its icy crust, based on gravitational measurements and geological models. Dione may also harbour a subsurface ocean, though evidence remains less conclusive than for other icy moons. The study of Tethys and Dione has revealed that ice moons vary substantially in their internal structures and surface features, despite their similar locations orbiting Saturn. The geological diversity among Saturn's ice moons demonstrates that even bodies similar in size and location can experience distinct evolutionary pathways. Mimas displays remarkable ice terrain, characterized by a massive impact crater that dominates its surface. The impact basin, named Herschel, is so large that the impact nearly shattered the moon, creating a crater surrounded by mountainous ridges and an unusual central peak. The heat generated by the impact that created Herschel likely melted the surrounding ice, allowing it to flow and reshape the surface. The interior of Herschel displays complex fracturing and features suggesting that the impact profoundly affected the moon's internal structure. Mimas orbits within Saturn's rings and may be responsible for maintaining ring structure through gravitational influences. The interaction between Mimas and Saturn's rings demonstrates how even small moons can exert significant gravitational influences on larger ring systems. The icy surface of Mimas reflects light effectively, making it one of the brightest objects in Saturn's system. The remarkable ice crater features on Mimas reveal the impacts that have shaped the Moon and the way impacts alter ice in extreme ways. Iapetus displays a remarkable two-tone appearance, with one hemisphere bright and the other dark, a stark contrast that intrigued planetary scientists. The bright regions consist of relatively pure water ice, while the dark regions contain heavily contaminated ice mixed with dark material. The boundary between bright and dark regions appears sharp, suggesting distinct geological processes create the two surface types. The dark material may be organic compounds created through radiation-driven chemistry on the surface, or material deposited from outside sources. The thermal properties of the bright and dark regions differ significantly, with the dark material absorbing more solar heat. The unequal heating of the bright and dark hemispheres influences thermal processes and may drive the migration of volatiles from dark to bright regions. Iapetus rotates synchronously with its orbit, keeping the same side perpetually facing Saturn, potentially contributing to the distinctive surface pattern. The two-tone appearance of Iapetus demonstrates that icy moons can develop remarkably asymmetric surface properties through geological processes. Hyperion displays an unusual spongy appearance, with low density and a highly irregular shape. The Moon appears to consist of loosely consolidated material with extensive internal pore space, creating a structure resembling a cosmic sponge. The loose structure may result from impacts that have fragmented the Moon and failed to completely reassemble under gravity. The composition of Hyperion likely includes ice mixed with rocky material, consistent with other Saturnian moons. The porous structure influences how the Moon responds to impacts and how material can escape when asteroids strike the surface. The irregular shape and chaotic rotation of Hyperion suggest that the Moon may be a fragment of a larger body disrupted through collisions. The study of Hyperion has revealed that not all moons possess compact, solid structures, and that some icy bodies can maintain low-density, porous configurations. The remarkable structure of Hyperion demonstrates the diversity of icy bodies and the complex processes that shape them. Phoebe orbits Saturn in a retrograde direction, suggesting that it originated far from Saturn and was captured into orbit through gravitational interactions. The dark surface of Phoebe indicates heavy contamination with organic compounds and other dark materials. The composition of Phoebe resembles that of icy bodies in the outer solar system more closely than it resembles Saturn's other moons. Phoebe likely migrated to Saturn's system from the outer regions of the solar system, perhaps captured from the scattered disk or Oort cloud. The ancient ice on Phoebe's surface may preserve chemical signatures from regions of the solar system far more distant than Saturn's immediate neighborhood. The retrograde orbit and dark composition of Phoebe have made it an object of intense scientific interest. The study of Phoebe contributes to understanding the migration of bodies throughout the solar system and the capture of distant objects into planetary orbits. Phoebe represents a visitor from the outer regions of the solar system, carrying ancient ice and organic material from its original formation location. Jupiter's moons display diverse icy compositions and surface features, reflecting their varied histories and current orbital positions. Io stands apart as the most volcanically active body in the solar system, its surface dominated by sulfur and sulfur compounds rather than ice. Europa harbors a massive subsurface ocean beneath its icy crust. Ganymede and Callisto possess icy surfaces with ancient cratering records and possible subsurface oceans. The density and composition of these moons suggest that ice and rocky material are mixed throughout their interiors. The orbital positions of the Galilean moons influence the tidal heating they experience, with innermost Io experiencing the most intense tidal stress. The study of Jupiter's icy moons has revolutionized our understanding of where liquid water and habitable conditions might exist in the solar system. The Galilean moons represent a microcosm of the solar system's diversity, with surface features and conditions varying dramatically among moons orbiting the same planet. Io contrasts sharply with the other Galilean moons through its intense volcanism and lack of significant surface ice. The heat generated by tidal friction from Jupiter's gravitational pull drives the volcanism that characterizes Io's surface. Sulfur and sulfur dioxide form the dominant surface materials, covering plains and creating spectacular volcanic features. The absence of substantial water ice on Io reflects the intense heat generated by the tidal forces and the chemical environment dominated by sulfur. Despite its proximity to the icy moons Europa, Ganymede, and Callisto, Io remains a fire world rather than an ice world. The contrast between Io and its neighboring moons demonstrates how orbital position and resulting tidal heating dramatically influence planetary body characteristics. Io's surface temperatures and composition represent the opposite extreme from the cold ice surfaces of the other Galilean moons. The study of Io, in contrast with the icy Galilean moons, illustrates the range of conditions possible within planetary systems. Ice on Europa's surface experiences continuous tectonic reshaping as the moon's crust flexes and cracks in response to tidal forces. The fractures and ridges that crisscross Europa's surface represent regions where the icy crust has split and slid past adjacent ice sheets. The motion of ice along these tectonic lines reshapes the surface continuously, creating a landscape in constant slow motion. The tectonic activity may facilitate communication between the subsurface ocean and the surface environment through cracks and fissures. The heat generated by tidal friction melts some of the ice, allowing it to flow and deform like a very cold but still somewhat plastic material. The study of Europa's ice tectonics has revealed that ice can be shaped through tectonic processes similar to those that reshape rocky continents on Earth. The tectonic reshaping of Europa's ice demonstrates that ice can be a dynamic material capable of complex geological behavior. The ice tectonics observed on Europa provide evidence that the moon's interior remains geologically active and capable of supporting dynamic processes. Europa's chaos terrain displays fractured, chaotic ice featuring block structures surrounded by darker material. These regions appear to be places where the icy surface has undergone recent disruption and possibly melting. The dark material filling the gaps between ice blocks may originate from the subsurface ocean or from material brought to the surface through upwelling. The chaos terrain is concentrated in regions where tidal heating is most intense, suggesting a connection between internal heat and surface disruption. The chaos regions may represent locations where liquid water from the subsurface ocean has recently reached the surface. The study of chaos terrain has provided crucial evidence that the subsurface ocean may exchange material with the surface environment. The fractured appearance of chaos terrain contrasts with the striated appearance of other portions of Europa's surface. The chaos terrain may be among the most promising locations to search for evidence of subsurface life if future spacecraft sample these regions. Red streaks appear across Europa's surface in intricate patterns that fascinate researchers and drive intense scientific curiosity. The reddish coloration marks regions where material from below the ice has been exposed or where chemical reactions have altered the surface composition through complex processes. These streaks may contain compounds created through radiation-driven chemistry operating on exposed minerals or material brought up from the subsurface ocean through cryovolcanic processes. The patterns form along cracks and fractures where the moon's icy crust has been split apart by tidal forces generated by Jupiter's immense gravitational pull. Some streaks appear fresh and bright, while others have been weathered by the intense radiation environment surrounding Jupiter. The composition of the red streaks remains partially mysterious to researchers, with spectroscopic analysis suggesting organic compounds mixed with minerals and possible iron-rich material. The streaks serve as windows into the chemical environment of Europa's subsurface and the exchange of material between ocean and surface environments. Scientists studying these features attempt to determine whether the red material originated from geological processes or from interactions with the cosmic radiation environment. The discovery of organic-rich streaks on Europa has heightened intense interest in missions designed to sample these regions directly. Ganymede possesses its own magnetic field, making it unique and remarkable among all moons in our solar system. This unusual magnetic field arises from dynamic processes within Ganymede's interior, possibly from convection in a partially molten core, or from intricate interactions between the moon's icy crust and its rocky interior. The magnetic field creates spectacular auroras at Ganymede's poles, similar to those that appear on Earth, producing displays of light in the thin atmosphere as charged particles interact with magnetic field lines. The interaction between Ganymede's magnetic field and Jupiter's massive magnetosphere creates a complex and dynamic electromagnetic environment around the Moon. The magnetosphere deflects charged particles from the solar wind, creating a protective bubble that influences radiation levels on the surface. The origin of Ganymede's magnetic field remains partially mysterious to scientists because the Moon should have cooled and solidified long ago, yet it continues to generate a measurably strong field today. The presence of this field strongly suggests that Ganymede's interior remains more dynamic and geologically active than expected and may harbor liquid water in subsurface regions. The auroras produced by Ganymede's magnetic field have been observed repeatedly by space-based telescopes and provide compelling evidence of ongoing geophysical activity. Callisto displays the most heavily cratered surface of any body in the Jupiter system, with impact basins overlapping each other in a landscape shaped by billions of years of bombardment. The thick icy crust has been saturated with impact craters, creating a terrain that appears ancient and undisturbed. Callisto's low density suggests that the interior contains a mixture of ice and rocky material, with possible subsurface liquid water in a deep ocean. The dense cratering record provides evidence that Callisto has remained geologically inactive for an extraordinarily long period, in sharp contrast to the active geologies of Io, Europa, and Ganymede. The ice on Callisto's surface shows evidence of sublimation and gradual alteration through exposure to radiation. The dark material covering some impact crater floors may indicate different compositions exposed from depth. Callisto's internal structure remains largely unknown, as the Moon lacks the tidal heating that activates other Galilean moons. The study of Callisto reveals that icy bodies can remain relatively dormant for billions of years, while maintaining subsurface liquid water beneath stable ice shells. Kuiper belt objects orbit far beyond Neptune in a region populated by thousands of icy bodies, each preserving pristine material from the solar system's formation. These small worlds contain complex mixtures of water ice, methane ice, ammonia ice, and rocky material accumulated from the early protoplanetary disk. The surfaces of Kuiper belt objects display diverse features, including impact craters, fractures, and unusual terrain shaped by slow processes operating over billions of years. Many Kuiper belt objects possess extremely dark surfaces covered with organic compounds, making them appear black despite their icy composition. The low density of many Kuiper belt objects suggests internal structures consisting of loosely consolidated material with significant pore space. The chemical composition of these distant bodies provides crucial information about the solar system's composition during its formation. The extreme cold at the Kuiper belt preserves volatile ices that would sublimate if moved closer to the Sun. The study of Kuiper Belt objects through remote observation and direct spacecraft encounters has revealed unexpected diversity in the outer solar system's small bodies. Sedna orbits in the distant outer solar system, in a peculiar orbit that carries it farther from the Sun than Neptune, yet brings it closer than typical Kuiper Belt objects. The extremely distant orbit raises questions about how Sedna reached such a position, with scientists proposing gravitational interactions with distant stellar companions or planets in the early solar system. Sedna's surface appears dark red, colored by organic compounds created through radiation processing of simpler molecules. The composition includes water ice mixed with methane ice and complex organic materials. Sedna's designation as a dwarf planet reflects its substantial size compared to most Kuiper Belt objects, yet it remains smaller than our Moon. The reddish coloration and organic content suggest that Sedna has been exposed to cosmic radiation for billions of years. The orbit of Sedna may indicate that the solar system contains more massive bodies in distant regions than currently known. The study of Sedna and similar distant objects challenges our understanding of planetary formation and migration in the outer solar system. Binary asteroid systems contain two rocky or icy bodies orbiting around their common center of mass, creating paired worlds that interact through gravity. These systems often form through collision and fragmentation or through capture of one asteroid by another over long periods. When ice exists within these binary systems, it must survive in the challenging environment created by gravitational interactions between the two bodies. The tidal heating generated by orbital dynamics can warm the ice, potentially creating subsurface liquid water in otherwise cold bodies. Some binary asteroids display asymmetric mass distributions and unusual shapes caused by tidal effects, reshaping the bodies over time. The presence of ice in binary systems affects the orbital evolution as sublimation creates no gravitational forces that alter trajectories. The study of binary asteroids with ice reveals how orbital dynamics influence the survival and evolution of volatile materials. Future spacecraft missions to binary asteroid systems will provide direct measurements of ice composition and distribution. Ice in regions of active star formation accumulates on dust grains and participates in the chemistry of young stellar systems. As newly formed stars begin to radiate intense ultraviolet light, they heat nearby dust and evaporate some of the surrounding ice. The evaporation of ice releases gases that become part of the circumstellar environment surrounding young stars. The interaction between stellar radiation and icy dust grains creates a dynamic chemical environment where complex molecules form and transform. Protoplanetary disks forming around young stars contain zones where ice can exist at specific distances, with warmer regions inside the disk and cold regions further out. The location of the ice line in a protoplanetary disk determines where solid bodies can accumulate and form plane, TS. The sublimation of ice contributes energy to protoplanetary disk dynamics and influences the orbital evolution of forming planets. The study of ice in star-forming regions connects planetary formation to the chemistry of interstellar space. Absorption lines in astronomical spectra appear when light passes through ice-containing material, with specific wavelengths of light being absorbed by molecules within the ice. Different ice compositions produce distinct absorption line patterns that serve as fingerprints identifying the molecules present. Water ice produces strong absorption features around 3 micrometers wavelength, while carbon dioxide ice produces lines at different wavelengths. The depth and shape of absorption lines provide information about ice temperature, thickness, and crystal structure. By analyzing absorption lines from distant objects, astronomers can determine ice composition and properties without direct sampling. The presence of absorption lines indicating ice in distant star-forming regions provided first evidence of widespread cosmic ice. The study of absorption line features continues to reveal new ice compositions and previously unknown molecules in space environments. Spectroscopic analysis of absorption lines remains one of the most powerful tools for studying ice throughout the universe. Infrared ice signatures reveal the presence of frozen materials through their thermal radiation at infrared wavelengths. Objects containing ice emit infrared radiation that reflects their temperature and composition, with different ice types showing distinct infrared properties. Water ice displays characteristic infrared brightness temperatures that differ significantly from rock or organic material. Carbon dioxide ice and methane ice produce infrared signatures that distinguish them from water ice. Thermal cameras aboard spacecraft detect infrared radiation emitted by icy surfaces, creating maps showing ice distribution and temperature. The infrared signature of ice changes with crystal structure and grain size, providing information about ice properties beyond simple detection. Infrared RAID observations have revealed ice in unexpected locations throughout the solar system, expanding our understanding of where frozen water and other volatile materials exist. The development of increasingly sensitive infrared instruments has revolutionized our ability to study ice in distant and cold environments. Spectroscopy of ice involves analyzing light that has interacted with ice in various ways, revealing the composition and physical state of the frozen material in remarkable detail. Visible light spectroscopy shows how ice reflects and absorbs light at wavelengths our eyes can see, producing color information about ice surfaces and surface properties. Infrared spectroscopy reveals vibrational modes of molecules within the ice, providing detailed compositional data about chemical species present. Ultraviolet spectroscopy probes the upper layers of ice and can indicate damage caused by radiation exposure and photochemical reactions. Raman spectroscopy uses scattered light to determine crystal structure and identify molecules with exceptional precision and sensitivity. The combination of spectroscopic techniques provides comprehensive understanding of ice composition, temperature, crystal structure, and formation history. Spectroscopic analysis of meteorites containing space ice has revealed the chemical diversity of cosmic ice that fell to Earth. The continuing development of spectroscopic methods enables scientists to extract ever more detailed and sophisticated information from observations of ice throughout the solar system and beyond. Ice crystal orientations in space can be organized by magnetic fields, creating aligned patterns within clouds of ice-containing dust. When dust grains coated with ice align with magnetic field lines, the crystals develop preferred orientations that influence how light passes through the material. The alignment of ice crystals affects the polarization of light traveling through space dust clouds. Astronomical observations of polarized light reveal information about magnetic field directions and ice crystal organization. The study of ice crystal alignment provides insights into the magnetic environment of star-forming regions and interstellar clouds. The organization of ice crystals through magnetic field interactions demonstrates how multiple forces shape the properties of cosmic ice. Measurement of polarized light from ice-containing regions continues to refine our understanding of magnetic structures in space. Sublimation processes in space occur when ice transforms directly into gas without passing through a liquid phase, driven by low pressure and radiation. The vacuum of space makes sublimation the dominant process for ice loss, as the low pressure prevents liquid water from existing on exposed surfaces. Radiation from stars and cosmic sources provides energy that drives sublimation by breaking molecular bonds in the ice. The rate of sublimation depends on temperature, radiation intensity, and the composition of the ice. Comets display dramatic sublimation as they approach the Sun, ejecting material at velocities that create the visible cometary tail. The sublimation process removes ice from bodies over billions of years, gradually shrinking icy objects and altering their composition. The pro: ducts of sublimation escape into space as gases that can be detected and analyzed by astronomers. Understanding sublimation rates helps predict the longevity of icy bodies and their evolution over cosmic time. Ice deposition in space occurs when water vapor and other gases condense directly onto cold dust-grained surfaces, forming solid ice without passing through a liquid phase. The deposition process builds up layers of ice on dust grains, creating the icy mantles found throughout interstellar clouds. The rate of deposition depends on the density of surrounding gas, the temperature of the dust grains, and the abundance of water vapor. The ice that accumulates through deposition preserves volatile molecules that would otherwise escape into space. The deposition process occurs continuously in cold regions of the universe, accumulating ice on dust grains at rates measurable through astronomical observations. The study of ice deposition processes has revealed how planetary bodies initially acquire volatile materials during formation. The deposition of ice on dust grains creates the chemical factory, where complex organic molecules form through radiation-driven reactions. Understanding deposition rates helps scientists model the accumulation of ice during planetary formation. Thermal cycling of ice in space occurs as bodies move through regions of varying solar radiation, experiencing repeated warming and cooling cycles over diurnal and seasonal timescales. Ice on bodies orbiting the Sun experiences intense diurnal thermal cycling as the sunny side faces the star directly, and the dark side cools rapidly to space temperatures. Seasonal variations in orbital distance create additional thermal cycling over longer timescales as bodies approach and recede from their parent stars. The thermal cycling causes ice crystals to expand and contract repeatedly, creating mechanical stress within the ice structure. Repeated thermal stress can cause fractures and cracks to develop in ice, altering surface texture and creating new grain boundaries and structural weaknesses. Weathering, caused by thermal cycling, gradually breaks down ice grains into smaller particles and exposes fresh material that has been protected from radiation. The study of thermal cycling effects helps explain the diversity of ice surface textures and surface roughness observed throughout the solar system. Laboratory simulations of thermal cycling reveal how ice properties change under repeated temperature variations in ways that closely match space conditions. Radiation effects on ice occur when energetic particles and photons alter ice molecules and create entirely new compounds through complex chemical reactions. Ultraviolet radiation from stars breaks chemical bonds in ice, releasing atoms and molecules that can recombine in new configurations and structures. Cosmic rays penetrate deeply into ice, creating damage tracks and producing reactive species throughout the ice structure. Solar wind particles strike exposed ice surfaces, sputtering away atoms and leaving behind chemically altered material. The radiation-driven chemistry on ice surfaces produces complex organic molecules that would not form under normal conditions in the absence of energetic input. The study of radiation effects on space ice has revealed that the ice is not inert or cheap, amically dead, but rather participates actively in ongoing chemical processes. The radiation processing of ice influences its color, reflectivity, and composition through continuous alteration and transformation of molecular structures. The products of radiation-driven chemistry in ice may have contributed significantly to the origin of life on the early Earth. Ice color changes in space result from radiation processing that creates organic compounds and alters surface composition in dramatic ways. Fresh ice appears white or blue due to water ice's inherent reflectivity and the scattering properties of ice crystals. Radiation exposure gradually darkens ice by creating organic compounds that absorb light more efficiently than pure water ice. The reddish coloration observed on some icy bodies results from complex organic molecules created through radiation-driven chemistry occurring over billions of years. The darkening process occurs at rates depending on radiation intensity, ice composition, and local temperature conditions. Ancient ice surfaces exposed to cosmic rays and ultraviolet radiation for billions of years can become nearly black or very dark. The color changes in ice provide visual evidence of radiation history and exposure age of the surface. The study of ice color variation helps scientists understand the radiation environment and exposure history of different solar system bodies and their evolution. Reflectivity of ice varies significantly depending on the ice type, purity, crystal structure, and surface texture. Pure water ice is highly reflective, bouncing back a large fraction of incident light in predictable patterns. The reflectivity changes substantially when ice becomes contaminated with dust or organic material, becoming darker and considerably less reflective. The reflectivity depends on the wavelength of light, with ice appearing different in visible light compared to infrared radiation. Surface roughness affects reflectivity markedly, with rough ice scattering light more diffusely than smooth polished ice. The age of ice influences reflectivity through accumulation of dust and radiation-induced darkening over time. Astronomical observations of reflectivity from distant icy bodies provide valuable information about surface composition and exposure age. The measurement of reflectivity at multiple wavelengths reveals important details about ice properties that cannot be determined from single wavelength observations alone. Ice grain sizes on icy bodies range from micron-scale dust to centimeter-scale particles, with size distributions influenced by formation processes and subsequent alteration mechanisms. Small grain sizes indicate recent deposition or active sublimation and redeposition cycles operating at the surface. Large grain sizes develop through thermal metamorphism and sintering over long time periods in protected regions. The grain size distribution affects how light scatters through ice and how the ice behaves physically under stress. Fine-grained ice appears whiter due to increased light scattering from numerous grain boundaries present throughout. Coarse-grained ice appears darker because light penetrates deeper without scattering at fewer grain boundaries. The grain size changes over time as solar heating and radiation gradually enlarge grains through thermal and chemical processes. The study of grain sizes provides important information about the thermal and radiation history of icy surfaces and their evolution. Ice erosion in space occurs through multiple processes, including sublimation, sputtering by solar wind, micrometeorite impacts, and radiation damage. The erosion processes remove material from ice surfaces at rates that vary with location and radiation environment. Solar wind sputtering preferentially removes atoms from the surface, creating a slight freshening of underlying ice. The erosion processes gradually expose new ice that has been shielded from radiation, bringing up material with different composition and color. The erosion rates determine how quickly volatile rich surfaces disappear and how long old materials remain exposed. The measurement of erosion rates helps scientists predict the survival of volatile materials in space. The study of erosion processes reveals the dynamic nature of ice surfaces, despite their seemingly stable appearance. The erosion of ice from the surfaces of small bodies gradually alters their composition and physical properties. Micrometeorite impacts on ice occur continuously as interplanetary dust particles strike exposed ice surfaces. The impacts create small craters and fractures that extend into the ice. The energy from impacts heats the ice locally, causing some material to vaporize and escape into space. The impacts create a regolith of shattered ice particles on the surfaces of icy bodies. The rate of impact damage depends on the location within the solar system and the population of micrometeorites in that region. The impacts expose fresh ice that has been shielded from radiation and sublimation. The study of impact damage on ice provides information about the micrometeorite environment and exposure ages. The cratering produced by micrometeorite impacts gradually alters the surface texture and composition of icy bodies. Ice sintering occurs when ice grains are pressed together and heated, causing them to bond and form consolidated structures. The sintering process removes pore space and increases density as grains fuse together. Solar heating drives sintering on the surfaces of icy bodies, gradually cementing loose ice particles. Sintering rates depend on temperature and the duration of heating. Deep within icy bodies, the weight of overlying material provides pressure that assists sintering. Sintered ice becomes stronger and more resistant to erosion than loose powder. The sintering process affects how ice behaves mechanically and influences its ability to support impact craters. The study of sintered ice helps scientists understand the internal structure and mechanical properties of icy bodies. Seasonal ice changes on Mars occur as carbon dioxide ice deposits accumulate at the polar caps during winter and sublimate during summer. The seasonal variations cause atmospheric pressure to fluctuate by about 25% annually. Water ice frost appears and disappears on exposed surfaces as temperature varies with season. The seasonal changes drive atmospheric circulation patterns and influence dust storm activity. The advance and retreat of seasonal carbon dioxide ice has been documented by multiple generations of Mars orbiters. The sublimation of seasonal ice at the South Pole produces upwelling of gas that creates dust storms visible from Earth. The study of seasonal ice changes provides information about Mars's climate and atmospheric dynamics. The accumulation and loss of seasonal ice helps scientists understand Mars's water cycle and volatile distribution. Martian ice clouds form when water vapor condenses in the cold upper atmosphere, creating clouds visible in orbital images. The ice crystals in these clouds scatter light, creating bright features visible against the darker surface. The formation of ice clouds depends on atmospheric temperature, humidity, and the presence of condensation nuclei. The clouds appear primarily in regions with higher elevation, where atmospheric temperatures are colder. The ice crystals gradually fall towards the surface, transporting water from the atmosphere. The growth and dissipation of ice clouds responds to diurnal and seasonal temperature variations. The study of Martian ice clouds provides information about atmospheric water abundance and circulation. The ice clouds contribute to the planet's radiation balance by reflecting solar radiation. Frost on Mars appears as white deposits on rocks and in shadowed regions where temperature drops below the frost point. The frost consists primarily of carbon dioxide ice during the cold seasons and water ice during other times. Hoarfrost deposits occur as water vapor condenses directly onto cold surfaces. The frost appears and disappears with daily and seasonal temperature cycles. Thick frost deposits visible in orbital images indicate regions of high atmospheric moisture. The sublimation of frost returns water and carbon dioxide to the atmosphere, participating in the planetary water and carbon dioxide cycles. The study of frost distribution helps identify regions where subsurface ice may be close to the surface. The properties of frost reveal information about recent atmospheric conditions and temperature extremes. Gullies on Mars appear as linear features carved by flowing material on steep slopes, suggesting recent water involvement. Scientists debate whether gullies formed through groundwater seepage, melting of subsurface ice, or even seasonal water flow. The gullies are concentrated in regions with south-facing slopes that receive maximum solar heating. The presence of gullies in regions with subsurface ice suggests a connection between ice melting and gully formation. The gullies display morphologies consistent with erosion by liquid water or water ice slurries. Recent observations suggest that some gullies may continue to form through active processes. The study of gullies provides evidence that liquid water or near liquid water can exist episodically on Mars's surface. The gullies offer tantalizing hints that ice-rich subsurface environments may be habitable. Recurring slope lineae are seasonal features that appear on steep slopes in Mars's southern hemisphere, becoming visible in summer and fading in winter. The features suggest seasonal flow of liquid water or briny water down the slopes. Spectroscopic observations indicate the presence of hydrated salts along the lineae, supporting a water-related origin. The lineae flow downslope in narrow channels, spreading out as they reach flatter terrain. The seasonal nature suggests that melting or seepage of subsurface ice provides the water source. The depth and intensity of lineae vary from year to year, indicating variable water availability. The study of recurring slope lineae provides evidence that Mars experiences active water processes despite its cold, dry climate. The lineae represent one of the strongest lines of evidence for recent or ongoing water activity on Mars. Mars Express has made discoveries about subsurface ice distribution through radar observations that penetrate into the ground. The spacecraft's MARSIS radar instrument has detected layered deposits containing ice in the polar regions. The radar reveals subsurface structure and water ice concentration at depth. The observations confirm the presence of vast ice reserves buried beneath Mars's polar regions. The radar data shows that some subsurface ice is relatively pure water ice, while other deposits contain mixtures of ice and dust. The discovery of extensive subsurface ice reserves suggests that water was more abundant on Mars in the past. The ongoing observations by Mars Express continue to refine our understanding of where ice exists beneath the surface. The radar technology employed by Mars Express provides a window into subsurface conditions inaccessible to surface rovers. The Phoenix lander sampled ice exposed at the surface in Mars's northern polar region, providing direct measurement of subsurface ice composition. The spacecraft dug shallow trenches that exposed white ice beneath the rust-colored dust. Analysis of the ice confirmed that it consisted of water ice similar to Earth ice. The lander measured the abundance of perchlorates in the soil, which can remain liquid at temperatures below freezing. The discovery of perchlorates suggested that water might flow transiently on Mars despite the low temperatures. The Phoenix lander provided the first definitive proof that subsurface ice exists at Mars's surface in accessible locations. The direct sampling by Phoenix demonstrated that ice remains preserved beneath Mars's surface despite billions of years of cosmic radiation and temperature cycling. The lander's measurements provided crucial data for assessing the potential habitability of Mars's subsurface. Ice beneath ExoMars rover sites will be directly sampled and analyzed by the rover's instruments as it explores the Martian subsurface. The rover will drill up to 2 meters into the ground, accessing ice that has been shielded from surface radiation. The samples will be analyzed for organic compounds and other potential signatures of biological activity. The subsurface ice offers protection from radiation that would destroy organic molecules on the surface. The drill samples will provide information about ice composition and the distribution of subsurface water. The rover's thermal analysis instruments will measure the temperature profile in the regolith and identify where ice transitions to liquid or vapor. The discovery of accessible subsurface ice by ExoMars will inform future human exploration strategies. The sampling of subsurface ice offers the best chance of discovering evidence of past or present Martian microbial life. The future of ice science lies in increasingly sophisticated observations and direct sample analysis from icy bodies throughout the solar system and beyond. New spacecraft designed to explore Europa and Enceladus will provide close-up views of ice surfaces and potentially sample material from subsurface oceans. Theoretical modeling of ice formation and evolution will continue to improve, allowing more accurate predictions of where ice can survive in various environments. The detection of exoplanetary ice through transit spectroscopy and other techniques will reveal the distribution of frozen water throughout the galaxy. Advanced laboratory simulations will recreate conditions of space ice more accurately, revealing chemical processes occurring in cosmic ices. The integration of observations from multiple spacecraft will piece together a comprehensive understanding of ice throughout the solar system. The potential discovery of life in subsurface oceans of icy moons will transform our understanding of biology's abundance in the universe. The study of ice will remain central to understanding the solar system's history, the present conditions of distant worlds, and the potential for life beyond Earth. Beneath the glowing gaze of distant stars, ice continues its patient transformation in the profound cosmic silence. You have journeyed through frozen landscapes, both near and impossibly far away, traveled through the vacuum's extreme and unforgiving conditions where water takes forms unknown on Earth. You have glimpsed the icy moons that harbor hidden oceans, witnessed the dust grains adorned with frozen mantles from which complex and strange molecules arise, and explored the exotic ices that paint distant worlds in colors we struggle to comprehend. The ice in space reveals itself through the patient work of scientists studying starlight and collecting precious samples, through spacecraft carrying cameras and instruments to realms where no human has ventured. Each discovery adds another thread to the rich tapestry of understanding how the universe creates and preserves water, how it builds the chemical foundations of life itself, and how frozen water shapes worlds beyond our own. The strange behavior of ice in vacuum and extreme cold, the exotic compositions formed under cosmic conditions, and the persistent presence of frozen materials throughout space demonstrate that ice is far stranger and more fundamental to the cosmos than our everyday experience with frozen water could ever suggest. If you have enjoyed this exploration of ice in all its cosmic variety and strangeness, I invite you to like, subscribe, or share your thoughts below. These quiet journeys of discovery reach others through your voice and choice to share them forward, one curious mind at a time. For now, let the image of ice-covered moons and frozen dust grains drift through your thoughts. Let the vast cold silence of space settle around you like a blanket, and know that beneath that cold exist possibilities for life and worlds we have yet to imagine. Rest easy. Breathe deeply. The ice in space waits patiently for the next explorer to venture forth.